So, good morning, everyone. Welcome to our Geo-Lesson webinar series. And in this lesson, we will be discussing an important and practical topic on how vetiver grass can be used for landslide management in a cost-effective manner on expansive soil. We are honored to have here with us Dr. Sadiq Khan, an associate professor in the Department of Civil and Environmental Engineering at Jackson State University. And Dr. Khan brings an extensive experience in geotechnical engineering, sustainable infrastructure, and innovative ground improvement techniques. So, from today's lesson, we look forward to have an insightful session that bridges research and real-world application. Thank you all for joining us today. Dr. Khan, the stage is yours.
Thank you, Adrika. Let me share my screen first. And I wanted to go from there. Can you see my screen?
Yes.
Let me try to. Hello, everyone. I'm going to talk about the vetiver grass and basically how we can utilize the vetiver grass for landslide management. It's a pretty long presentation, so I'll try to cut it a little bit short and try to go a little bit faster. So in our Create lab, we are working with the vetiver grass for a very long time. And I personally feel like this is a really good time for us to to present what we have done and how we should be working with it. So since we are talking about the landslide management, there are a few things that is super important to understand, and that's why we wanted to highlight a couple of the study we have done before and from our lab. One is the Steady Study 286, and then the other one is the Steady Study 316. I really encourage you to go and check these. Both are publicly available reports, and you can find out like the findings of how the landslide happens, and there are like many different techniques that can be used for that. Sorry about. And before I wanted to go into the landslide management, I wanted to talk about how we can utilize the vetiver grass for the landslide management. I want to talk about a few things, especially targeting the expansive soil. And in terms of the expansive soil, if you know about the expansive soil has a behavior that calls shrinkage and swelling behavior. So with the shrinkage and swelling behavior, the way it works is every time the expansive soil get exposed to water, it absorbs water and it swell. And then when it becomes dry, it loses water and it shrinks. So every time the wet dry cycles, the shrink swell behavior takes place within the clay, and because of that, the shear strength of the clay changes. So think about, we have a highway embankment which contains expansive soil. And if the highway embankment contains the expansive soil, the shear strength at like when the embankment is being constructed will be pretty high. And at that time, the shear strength of that slope or the embankment should be close to the top line, which is the green line here. But what will happen is like if the expansive soil get exposed to different wet dry cycles, the shear strength will keep dropping, and the lowest possible strength that we can get out of it is known as the residual strength. So residual strength is at where the soil started moving. So basically, we usually have a peak strength, and then after the peak strength is like when the soil usually have the shearing, the there is a reorientation of the soil particles, and because of that, the shear strength drops significantly, and we can find it out from the direct shear test or ring shear test. And in between, what happens is like if you have if we test different samples at different wet dry cycles, what we can see is once after construction, if a sample exposed to different weight dry cycle. For example, here we are showing the three number of weight dry cycle. The shear strength drop from the peak strength, and it reaches close to the fully softened strength. The fully softened strength line is the purple line, and then it will keep dropping to like and keep trying to reach to the residual strength. So every time when the soil is being exposed to a different type of the weight dry cycles, the shear strength keep dropping. So when the shear strength is dropping, the factor of safety of the soil will keep dropping. And if the factor of safety of the soil keep dropping, the slope uh, will reach close to the like marginal condition. If it get exposed to the rainfall, the condition will get bad. And at the same time, I wanted to emphasize another thing, which is the like micro structure of the soil. So if you look into the microstructure at different weight dry cycle, including the 3, 5, and 7 number of weight dry cycles, you can see is like how much volume of the void we have within the soil. So let's say if it is a 3 number of weight dry cycle, there are like certain amount of void. With the 5 number of weight dry cycle, the void volume goes up, and with the 7 number of weight dry cycle, the volume of the void goes even higher. So there are like the void ratio of the soil goes down, and the volume of the void goes up when the soil goes through a certain number of weight dry cycles. And if there is a certain number of weight dry cycles, the shear strength goes down for sure. But the another thing that also changes, which is the permeability goes up. Now, if the permeability goes up by that time, uh, what will happen is soil like a slope that contains expansive soil and has a high amount of wet dry cycles or high amount of like permeability in it. When it get exposed to the rainfall, it will have some challenges. And this is what we have noticed from our field study. We look into a field study which is a Terry Road, where the like inclinometer, we can look into the inclinometer results, and then we can also see is like how the matrix section and the moisture content is changing. And then we can also see is like how the like how the moisture is being held within the slope at different time, and how this moisture is keep increasing. And then we also have done some modeling in our lab, and from the models we can see is like there are a significant increase in the soil moisture, and due to that, the factor of safety of the slope keep dropping when the slope get exposed to a certain number of rainfall. So basically, what is happening is the slope will get to a condition where there is a development of a perch water. And if there is a perch water condition development, usually that happens within the top few feet. And if the perch water is sitting there within the top few feet, that also creates some additional challenges. That includes like it create additional force for the slope, so the slope started moving, and it also make the condition very marginal. So in a nutshell, if we try to combine it all together, what will happen is like with the expansive soil like Yazoo clay, what we have in Mississippi, uh, we can look into like the difference, and then at different time with the exposure to the like different wind dry cycles, the Sherston drops. And if we integrate that number, we can see is like how the factor of safety keeps dropping with a different number of cases. Here we can see a result from a rainfall simulation where we have like a slow and sustained rainfall for a given time. And for the slow and sustained rainfall with the like 7 number of weight dry cycles, we can see the factor of safety reaches very close to 1. So we can consider it like this is kind of like a situation which will trigger a landslide on that particular soil. So technically what happens there is like if we can just go back and find out what is the conditions of the slope, and then if we can find out like how much rainfall is there. So we need to know the shear strength, we need to know the rainfall, we need to know the permeability behavior. We can do some kind of like infiltration modeling, couple flow deformation analysis in any of the software package like Plexus, GeoStudy, or anything else. Then we can find out of how that slope is going to fail, or like what is the most marginal condition is going to be there. Once we find that out, then we can look into like the overall condition where the soil will have a perch water. Because of this perch water, the slope is started moving, and then we need to find out like some kind of like the solution into it, and that solution will help us to define how we can mitigate that, and how we can reduce the whatever the strength degradation we are facing, or that the soil is losing the shear strength. So basically, we need to find out an optimum solution. There are many different solutions for that. Reinforcement is one of that, like piles. We can use the piles, we can use soil nails, we can use recycled plastic bin, we can also use different other conditions like uh, the like horizontal drainage and so on. And in reality, there are like many different techniques that already has been used to geogrid, and geostabilization is another one. And all of them has been proven very well. The only challenge is we don't have any solution in the market which can satisfy few criteria. Number one is it doesn't increase the shear strength, and it reduces the like the moisture from the soil. So, and then we don't have any solution that is also extremely cost effective. So because of that, most of the cases, even if our agencies, many agencies knows that there is some kind of landslide, and the landslide is not work, is landslide is there, but it's mostly being unattended, and mostly is being unstabilized. The reason is whatever the solution we have currently in the market, none of them can be done in a proactive manner, in a cost-effective manner. So those are not a viable economic solution given that problem. So to make a solution viable, economically viable, we need to wait till the the problem becomes so big that the the repair becomes economically viable. So, and that's a more of an economical problem than it's an engineering problem. So whatever the way it works, let's say we have a landslide, and if that landslide is sitting somewhere, someone knows there is a landslide, but no one can fix the landslide because it's not economically viable to do that, because we cannot spend 10 like $100,000 to solve a problem that didn't happen yet. It's a change in the mindset. So and then there are like different need and so on. And our lab started working on it, and our lab look into that problem, especially how we can make it work. So out of it, what we came up with is basically using the vetiver grass, which makes this uh, which makes it a really great solution for the given problem. So again, I wanted to go back to what we are talking about in terms of the economics. So in terms of that, let's say there is a landslide. The landslide is in a certain condition that is gonna fail, not gonna fail immediately, but gonna fail in like, let's say, next 3 to 5 years. So if that landslide is happening in next 3 to 5 years, and we keep it unattended, the problem, which is maybe $50,000 now, will be $1 million problem after failure. Because if we can repair a landslide before the failure happened, then we don't need to do any earthwork. We don't need to do the traffic control. We don't need to do the excavation, backfilling, and any other activities. We don't need to do the all sort of the investigation. So we save a tons of engineering cost. We save a tons of the time, and we will save a tons of money in the construction. And then if we can come up with this easy solution, which can be just planted, that has a great economic benefit. At the same time, we also need to find out if we have a solution like a grass, like a vetiver grass, will it be viable? Or if it is viable, then how to make it work? So there are like many different things that are going to connect the dots here. So we started the project, and this project is funded primarily by National Science Foundation and also funded by Mississippi Department of Transportation. And through this funding, we're able to look into different options and finding out like how the vetiver grass works and so on. So in our cases, we've primarily considered that vetiver grass will give us three major benefits if we try it out on the expansive side. The first benefit we're gonna get is in the expansive soil, there are shrinkage cracks, and the root system should be helping us to reduce the volume of the shrinkage cracks. That's number one. Number two, we need to look into how we can utilize the vetiver grass to reduce the soil moisture content within the slope. So that is our number two. And number three is we also need to find out how we can utilize the vetiver grass to increase the shear strength of the slope. So in terms of increasing the shear strength of the slope, we can utilize the vetiver grass in terms of like as a bioanchor, or it can directly be used just to reduce the shear, just to increase the shear strength, considering RAR method, which is the root area ratio method. So we look into all of that. So first of all, I wanted to give you some background on the vetiver grass. Vetiver grass is uh, like it's a grass, perennial grass that has a root system that grows very deep. Easily within a couple of years, the root system grows up to 10 to 12 feet. Sometimes based on the soil condition, water content, and all sort of the condition, the root system can grow up to 15 feet. This is how what we have noticed in the literature. In our results, we found it up to 10 feet. And then this is the photo from one of the site where we tested out vetiver grass into the levees. And we have seen like how the vetiver grass worked within the levee system. So where to use the vetiver grass and how the vetiver grass can be used. So vetiver grass has been tested within this region, like the yellow mark area, based on the literature, based on our test results, and based on the plant hardiness zone map. But at the same time, I also have received information and call from the people and some of the farmers who tried out in New Jersey. They tried out in Pennsylvania, and they also tried out like in other countries, especially in China, where the climate condition is very cold. Usually in the literature, it says that vetiver is not a cold tolerant plant, but many people tried vetiver in those areas and it survived. Uh, Based on the literature, vetiver doesn't survive in any uh, frost condition, and that really makes sense. So the root system dies in a extended frost condition, but wherever we tried vetiver grass in Mississippi, we faced some significant snowstorm over the years, and every time the vetiver survived those snowstorms, and we haven't seen the vetiver died, meaning that the vetiver system worked, and once it established that the root system, it can survive in the cold condition too. Uh, but we need more test results to validate that. We have done growth study on vetiver different conditions, and I want to acknowledge Oviprio for that. Oviprio has done a great work on it, and Oviprio, and with the help of our great team, we are able to plan vetiver, test it out in the laboratory settings and in the field settings. And then what we did is like we planted we have taken the vetiver, we have the root system, and then we did a modification in the like in the direct share equipment, and then within the direct share equipment we try to test it out and try to see is like how does strain the vetiver grass can take. And This is the test result primarily done by Viprio. So he has done it on the clay and water. And we have seen is like how much strength gain vetiver crust can have. And in our analytics, we primarily faced like we are vetiver crust can have like a very high tensile strength uh, when they are very young. So because what happens is like when the vetiver crust is young, it acts like very ductile and uh, its load carrying capacity is not very high, but its tensile capacity is very high. And this is, or like the tensile strength becomes very high. On the other hand, if we try out vetiver in uh, like in a mature plant, then the load carrying capacity goes up significantly because the diameter of vetiver is pretty high. And because of this diameter of the vetiver, we can also look into uh, like how vetiver is uh, working into the clay versus sand. And the basically the strength characteristics of vetiver changes over the years. And then we also look into uh, the the vetiver growth in the like in the same slope, the Terry Road, and in that one we have seen the vetiver grows up to 10 feet, and here we can see is like the roots right here. Then we also look into the vetiver grass and the its root, like the root morphology at different conditions, especially in clay and sand. And if we look into the root system, the way it works, the diameter of the root becomes much higher when it grows in clay versus the diameter is lower when it grows in sand. So if you look into the width of the vetiver, basically we can see is like the root system becomes right here. This root is close to like a zero point 0.5 millimeter or so, and in this case, this root becomes like close to 2 millimeter. And then since the diameter goes up into the clay soil, the load carrying capacity is much higher, and that is very important. If the But at the same time, the total number of root goes down. So there are three things. The first one is the individual load carrying capacity of one root. The number of root that we have in a soil condition, and then the total load carrying capacity. So if we have the clay, the individual strength of the root becomes very high, but the total load carrying capacity remains fairly same. So because what happens is in the sand, the individual diameter of the root is lower, but the number of root is higher. So it kind of balances out that. And here you can see is like the type of the root in the clay, sand, and fresh water. And into the fresh water, you can also see is like how the vertebrate grows in the fresh water versus how vertebrate grows in the clay. And in the clay, you can see is like those roots are very thick, and in the water is very thin, in the sand is in between. And we also noticed that this is a very high adaptive characteristics of vetiver grass when we wanted to do it at different soil. So in the clay, usually soil don't have much oxygen in it. So if soil doesn't have much oxygen, uh, it is quite difficult for the plant to survive. And plant has to also try to go deeper to get the water. So basically what happens is when we try this plant in the clay soil, those are compacted clay. So to penetrate into the compacted clay, the root system has to be much stronger. When we try it out in the sand has many void. So a plant doesn't has to fight to grow the root system into the sand. And that's why the system can grow there very freely, and it also survives there. Then we have done the Drake shed test. It's primarily the work done by Viprio. And so basically on that cases, we developed the Drake shed test. I think this is the overall setup. This is the physical Drake shed test that we fabricated in our lab. And then we tested it out. So in this case, it has like 4 LVDTs. And then we also have like the load cell, and then we also have the weight on top. I wanted to emphasize it why we need 4 LVDTs instead of just 1 LVDTs. So the way it worked is if we have only 1 LVDT, when we are trying to push the vetiver can turn around. So basically the whole box, when we are trying to push it, there might be some kind of rotational movement instead of the translational movement. So we wanted to make sure that in our loading cases, we are just doing a translational load, not the rotational load. And we wanted to make sure that the translational load is what happens during the landslide, not the rotational force. And basically for the plant, the it kind of like the torque versus the shear capacity is different. So we wanted to make sure that we are primarily creating the shear here, not any kind of torsion. And that's why we used 4 LVDTs to look into that. And then we try to control that when we are loading it or trying to failing it. So here is a video of, I guess there is a video that it shows like when we're trying to push it and how does it work. And here is the fail, like here's the failure results and how many, like we can see is like how many roots into it, and you also can see that the sharing at this point. So the sharing at this point is kind of like quite visible here at the bottom. And then you also can see is the root system that has failed. So that root system is also quite visible here too. And then here are the test results, and using the RAR method, we can see is like this is the condition without vetiver, and this is the condition with vetiver. Then we also did the rainfall simulation to test our second hypothesis that if we plant the vetiver should pull out enough moisture from the slope and it should dry out the slope. And because of that, we should be able to find it effectively. So these frames are primarily made by Amber at the beginning, and then Richard take it over. I believe Asif and Rahul was also involved in those testing from our team. So in these cases, we have tested the rainfall and we simulated rainfall on top. And then we have different rainfall intensity, especially in this case, we have 1 to 1 slope, which is 45-degree slope with the rainfall intensity from 0.47 inch. And we have simulated it for 8.5 hours. And then we look into like the volumetric moisture content. We also look into the matrix section, and then we also look into the overall rainfall volume. And then once we simulated that, we are able to see is like this is the time when we simulated the rainfall. And after the rainfall simulation, the moisture content goes up significantly, and it was holding it. The primary reason it was holding the moisture content because of the soil is clay, and it tend to hold the moisture for a long time. But after that, usually what happens is like based on our result, what we have seen from the field study, whatever, like in the yazoo clay or a high expansive soil, water tend to be there for a very long time because water doesn't drain out. It kind of sitting there and it should be there for long. But once we planted the vetiver grass, it is a game changer because what it does is it's kind of try to pull off the moisture from there. And when it try to pull off the moisture from there, the moisture content keeps dropping. And I personally feel like this is extremely helpful for the slope because if when it reduces the moisture content, the overall dynamics has changed, and the dynamics really helped us to mitigate the like slope failures. And I personally feel the instead of the shear strength, like utilizing the evapotranspiration is a better approach into the slope management than just relying on the shear strength of the slope. Because when we are trying to utilizing the evapotranspiration characteristics of the the plant, what happens there is it not only draw the moisture from the soil, it also reduces the load because now the unit rate goes down when it pull off the moisture from the slope. And then at the same time, the matrix section goes up significantly. And if the matrix section goes up significantly when we reduces the moisture content, it primarily helps us to mitigate the slope failure because it increases the shear strength of it. So in this case, if for the same slope, we have a simulated rainfall. And with the simulated rainfall, we are going over on top, and we can see is like how much rainfall is there. And because of those rainfalls, uh, like the overall drop in the metric section. And if we look into that, it shows us like the gaining of the marsh of the metric section from the slope because of the evapotranspiration action of Vetiver. So if you look into the data, what happens is like due to the rainfall simulation, the matrix section drops significantly, it becomes close to zero, and then over the period of time, whatever pull of the moisture, and when whatever pull of the moisture, the matrix section goes up pretty high. So when the matrix section goes up pretty high, the shear strength goes up higher. So the factor of safety, the gain in the factor of safety is much higher in this case because we are uh, utilizing the evapotranspiration action of the slope. Then we have done the field evaluation. I'll cut to the field evaluation part and I'll try to go over my presentation pretty quickly from now on. And because there are like few different case studies we have, and I wanted to finish it in next 20 minutes. So we have tried out vetiver grass in different slopes, and the first one is on the Terry Road, where we have the data. Terry Road is like 3.524 to 1 slope. And then in this one, we planted vetiver here. And then we planted the vetiver in this section. It's a small section when we started the project on June 2020. And then how does it looks like in July 2020? And you can see that it's a proof of the vetiver growth in the expansive soil. And this is the first time we try vetiver on any expansive soil. And we got very excited that the vetiver works really well in it. And then this is the overall site condition between like 2011 and 2024. So there was like a pre-existing failure on the slope, and then we tried it out vetiver at this location. Uh, and this is how it looks like, but we're in different conditions where at the beginning we kind of try to hold the slope and not mowing it, but it's kind of having the mowing and it looks pretty clean. And here we have the different instrumentation. Here our team collecting the data from the slope, and this is how it looks like in terms of the soil moisture content and the matrix section variation. I want to emphasize it that these sensors are installed at 6 and 18 inch. We just wanted to see is like the overall variations from the surface, and then we also wanted to see the variations in terms of the like in between different timeline. And here we can also see is the variations of those locations. I think it's the same slope, and then we are also looking into the suction variation here. So with the suction variation, we can see is like with the vetiver, it pulling off the moisture, the suction goes down. But you have to remember in Mississippi there are like a lot of rain, and because there are a lot of rain, we usually it's a very superficial, so the moisture recharge becomes very quick in this area. So even uh, the vetiver was able to pull up the moisture because of like these conditions, but later on there are like a lot of rain and it can kind of reinforce back. In this case, we are looking into the inclinometer data from the slope, and from the inclinometer data, we also have done the ERI in this case, and this is primarily the work led by Fariha. So in this case, we have done like two lines in the line A, and we have like three lines. We have line A and line B on the top and at like near the toe, and then we have a line C that is close to this section. So this is the line C. And if we look into the results of the line A, this is a very interesting results. You can see what is happening here is when we are trying to look into the change detection into a condition, what happens is in the expansive soil, we always have seen that the slope has a very high moisture, especially in Mississippi. And because in most of the cases, we have like a lot of rain. And when we have the rain, the water gets in, and when the water seeps in into the expansive soil usually keep the water and didn't let the water drain away. So basically, it holds the moisture, and the holding the moisture is pretty common. But when we planted vetiver in this section, you have to remember that this is a very small section where we planted the vetiver, and the vetiver kind of like reduced the moisture content at the bottom, and we have seen a very interesting change. Instead of like seeing the changes on the top, which is there, we also have seen that the bottom part of that slope is getting drier. And this is an amazing result from the viewpoint that if we just change the overall water dynamics or the water balance from the top, the bottom part of the slope, if it doesn't have a groundwater table, get it used to get dried out. Because what happens there is like there is always a certain water recharge from the top, and then the water seeps down and it's a settle down at the bottom. But if we stop or reduce the amount of volume of the water that is coming from the top, then what happens there is like there is a trickle down effect that goes down below the slope. And when the trickle down effect going below the slope, it's kind of making it drier. It will take some time. It's not a short-term benefit, it's a long-term benefit. And if we are getting the long-term benefit out of it, it has a very significant benefit in terms of the deep-seated landslide management, because this can be used very effectively in a hilly condition where we might have a, the vegetation on top, and then usually in many cases it creates some kind of deep-seated failure. But using this phenomena, we can try out Vetiver for some kind of deep-seated slope management cases. And if we wanted to utilize it for some kind of deep-seated slope management cases, this is something we can, uh, this is the proof that we have that Vetiver really helped to reduce the moisture content below the ground. It's not only the influence area where the root system is, but it goes below there, and it's kind of help us to mitigate that. And that's something is very useful. Then we also have the vetiver planted section. It is again is from line A. This is the results from line B, and from the line B we can see the similar condition where we can see is like the bottom part of this slope is like the factor, the resistivity value is increasing. And when the resistivity value is increasing, in these sections, this resistivity value was pretty uh, pretty low. It's like if you look into that number, this number is like close to 3.34 or so on. In this case, this number is increasing. And with the line B, it is still has some increment, but again, there are like some drops in it. So there might be some other scenario. Line B is at the bottom, right? So if the line B is at the bottom, they might have some kind of uh, there might be some kind of leaking there, because what happens there is like in this is very close to the roadway, and in this area in Mississippi, usually we have like the water pipelines, so the water main, and because of the water main, there are like some leakage into the water main, and that's another problem of the aging infrastructure, which also make problem for the slopes. So because of that, there is a high likelihood there is a high amount of water that is coming in and holding it to there. We have the field instrumentation at that slope using the LiDAR and drone survey. So I just wanted to show you some of the results from our lab in terms of the LiDAR and drone survey. So you can see it's like how uh, the digital train model looks like from the drone survey, and then this is the 3D LiDAR scanning from is basically the 3D LiDAR scanning here. And you can see it's like from there we get to the point cloud, we can cut the sections, we can put it on top of each other and monitor if there is any kind of slope movement or not. And from from those results, we can find out like, no, there is not much changes from the Vetiver that is coming in here. And then we have done the slope stability analysis on the terry road slope again. And if we look into that with and without vetiver grass, then basically what happens is before we plant the vetiver, we can see that there is a substantial amount of moisture that is sitting here that we haven't seen like much changes on it. But if we plant the vetiver with vetiver grass, it has the evapotranspiration. We incorporate the evapotranspiration into the analysis as well as the shear strength like increase. And from there, we can look into the like a coupled action of the bio anchor and a vertical drain. And if we integrate that, the factor of safety of the slope goes from 1.05 to 1.6. This is a very low-cost solution. It can be done very effectively. We just need to find out like when the slope becomes in a marginal condition, and when the slope reaches into the marginal condition, we really have to look into like some kind of crack development or some kind of like some depression into the ground. So those are really the early detection of the marginal slopes. And if we can just go there where the slope didn't fail yet, and if we plant the vetiver grass, we can mitigate those slope failure problems. And it's a great low-cost techniques that can be implemented for a very large scale slopes, and it really helped us to reduce the cost maybe 80%. Then it will be needed if the slope has failed. So I talked about the economics of or the viability of the economics for a given landslide, which haven't failed yet and going to happen. So if that landslide didn't fail it and we wanted to do some kind of repair in it, we really have to see is like when and what is the timeline we should target it to repair those slopes. And in this case, we need to run some investigation back analysis, and then we need to find out the optimum condition. Based on that, we can help in terms of how to plant vetiver, how to grow, and so on. So if you're watching it, please feel free to contact uh, to us, and we will be very happy to collaborate with any of you. Thank you so much. I wanted to end my presentation here. I think it's 11:47 in the central time. So I want to stop it here, and then I wanted to open it up for the questions. Thank you, Atrika, for the opportunity.
Thank you, Dr. Khan, for your insightful presentation. So, as Dr. Khan said, we are moving into the question answer session. If you have any question, please feel free to ask.
Dr. Khan, I have one question.
Sure.
So the slope that has existing uh, cracks, like big cracks, how Vetiver helps to mitigate that problem or against erosion against those kind of slope, like the slope that has failed already has crack and already vulnerable to erosion, infiltration as well. So how Vetiver helps in those kind of condition, like for shallow slope failure?
Well, this is a great question, Rahul. Thank you for asking. Basically, what happens if a slope has a crack, like a tension crack, then the tension crack easily let the water gets in, and then basically increase the driving force. The water will try to push the slope, and that will eventually create a landslide. So in this case, what we can do, if you plant the vetiver grass, vetiver will first of all increase the shear strength. Then vetiver will try to hold the slope in place because of the uh, the bio anchor action. And then vetiver will also drain out the moisture when the soil goes through the crack. But my recommendation would be first we should fill the crack with the soil, and then we should plant the vetiver. We should not keep the crack open. If we keep the crack open, it's not a good idea because that's something that will increase the moisture infiltration. That's one thing. Another thing is, let's say if we plant the vetiver grass in expansive soil, then vetiver will also reduce the propagation of the crack because it works like a fine reinforcement or secondary reinforcement within the soil and try to keep it in place. And because of that, that it doesn't let the expansiveness like action takes place to increase the shear strength. So it's basically it create a inner reinforcement that will reduce the crack volume. And we also have tested that, and that result is already been proven in our case.
Thank you, Dr. Khan.
Thank you.
I have one question. So, what is the impact of vetiver in the deep-seated failures? If it will help anything on that?
That's another great question. Uh, Vetiver will help reducing the formation of the deep-seated failure. It will not mitigate the deep-seated failure because the root grows up to 10 to 12 feet, but it definitely helps to undo the soil moisture balance. So when it undo the soil moisture balance, what happens there is it reduces the amount of water infiltration into the slope, which basically goes down deeper and create a imbalance. So reducing that moisture volume helps in terms of the deep-seated condition. And then Vetiver can be a really great tool for value engineering when we do it with any other solution that is very effective for deep-seated failure, like H-pile or drill shaft or anchors, like the long anchors or the soil nails. So basically, whatever the way it can be done is like whatever can reduce the amount of the soil nail and the anchors needed, and basically that will cut off uh, the cost significantly.
Dr. Khan, I have a question.
Sure.
If we use vetiver grass for landslide failures, like to prevent landslide failures, what is the difference in cost other than
In,
using the traditional methods?
well, it depends on when we're doing it. So if we are doing the landslide repair before the failure happens, the cost savings is going to be 80 to 90% with any traditional techniques, because most of the traditional technique cannot be used for this, for the proactive repair. Most of the techniques has been designed for reactive repair. So the Vetiver can be the solution for the proactive repair. If we are looking to Vetiver for reactive repair, then we need to look into the other things as well. For example, if we're comparing it with H-piles or recycled plastic bin or any other established method, then what happens there is there is a cost involvement for the like soil, like for earthwork and compaction and rebuilding the slope. So that has a cost. That cost goes up. But in terms of planting the reinforcement, there would be a reduction of the cost and the time. So we can consider that with the Vetiver, the cost savings will be around 50 to 60% compared to other techniques, any techniques. But it depends on like for the timing. So if you really wanted to save the numbers, Vetiver can be a significantly game-changing tool to make it proactive. It's not easy to be proactive for slope repair, and Vetiver can change this game on that.
Thank you, Dr. Khan.
Sure.
Is there any more questions from the participants? So if there are no more questions, we have almost reached the end of the webinar. And once again, thank you, Dr. Khan, for taking the time for sharing your knowledge with us today. It was really an interesting topic, and I'm sure everyone learned something useful today. And thank you to all the participants also for joining and being part of the discussion. Just a quick reminder that whoever joined this session will get a 1 PDH hour automatically. But for those who couldn't join, this video will be uploaded in LinkedIn, YouTube, and our website. You guys can watch the video, and there will be a PDH assessment. And after attending the assessment, you can get the PDH hour. We really appreciate your time, and we hope to see you in our upcoming Geo-Lesson webinar, which will be hosted in the last week of May. And we will share the details of the webinar of May in our websites and LinkedIn and our social media pages. Thank you, everyone, for joining. Dr. Khan, if you have anything to say.
And thank you so much. I really appreciate it. And I think it has, this is a topic we should push more. So maybe we can have another presentation in terms of the field studies, because today I covered really like very short field study of that, and the lesson learned from all of our field studies, we should do another one. That's my take on it.
Sure, Dr. Khan.
Sure. All right. Thank you so much, Atrika. Thank you so much, all.
Thank you.
Thank you, Dr. Khan.
Thank you.